Let me start recording now. All right, so again, the definition of continuity is if you have a function f, and we want to see if it's continuous, that means it's a smooth curve. There's no holes, there's no gaps, there's no breaks. It's a smooth curve at some point c, at some location x equals c. We want to know, does it connect at that spot? The definition of continuity says you test the limit from the left and the limit from the right. If the limit from the left is equal to the limit from the right, is equal to the value at that spot, meaning if they connect, then f of x is continuous at that function c. Sometimes this is called the three-part definition. Sometimes this is called a three-part definition because there's three pieces that need to exist. Three sort of steps that need to be true. The limit from the left, the limit from the right, and the value itself all need to match. And if they all match, then you have a continuous function at that spot, x equals c. The example given here is like a bridge, right? Imagine there's a bridge. So the limit from the left, right, approaching, this is the limit as x approaches c from the left. And then you have the limit from the right. Limit from the right as x approaches some value c from the right. And then you have the value itself. This is f of c. F of c, plugging in that c spot. So you plug in the number and you see if it works. And if they all match each other, the limits exist and they match, then you have like a smooth curve. That's how you drive, right? How you drive over things. There's no break, there's no gap, there's no hole, you're not going to fall to your doom. The car can drive over the gap, the car can drive through the bridge, connecting these two sides of the equation together and being continuous. Don't make your car fall down. Limit from the left, limit from the right, and the value itself. This three-part definition. And it's critical to know this definition because you will be asked more than once, whether something is continuous, and it matters. Continuity matters in AP Calc because certain functions work certain ways if a graph is connected. Basically, continuity just means there's a smooth curve. There's no weird asymptotes. There's no holes in the graph. There's no what is the other kind of continuity? The jumps. There's no jumps. Nothing strange is happening. We want a mathematical definition of what it means to be a smooth curve. The whole point of continuity is just ensuring that we have a definition of what it means to be smooth. Continuity equals smooth. That's the definition of what it means to be smooth. So, how do we use this definition? So here's an example. How do we use this? In example 6, the question says, using the definition of continuity, which is the three-part definition, determine whether the graph of h, this equation here, is continuous at the following values. And you have this word here, justify. In AP Calculus, when you are asked to justify, it means you must justify mathematically. That means you need to use definitions. Use the rules that you have, that we've talked about. Use, I should say, math definitions. Definitions. So we want to know if it's continuous. If it's continuous, using the definition of continuity, is it continuous on these three spots at x equals 2, 0, and -10? So we need to figure out what is going on with this equation at these various locations. And as we know, to figure it out, we take this function and we start to break it apart. We start to factor it apart. X cubed minus 4x on the top, and x squared plus 8x minus 20 on the bottom. So we're going to factor this apart. On the top, well, let's do the bottom first. That's pretty easy, right? We have a trinomial. Break apart the 20. 20, I can have 1 and 20, 2 and 10, 4 and 5. What's going to make 8? I think the 10 and the 2, right? So I'm going to have 10 and 2. And I'm going to have positive 10, negative 2 to make positive 8. So it's going to be x plus 10, x minus 2 on the bottom. Let me give myself a little bit more room. X plus 10, x minus 2 on the bottom. X plus 10, x minus 2. Right? So that's the bottom. What about the top? What can I do to factor this top part? Well, first thing you should notice is x cubed and 4x, they both have x's. We can have a GCF. I can factor out a greatest common factor of an x. And then I get x squared minus 4. So I got my factored out x, x squared minus 4. Can I go any further? Am I done here? Am I stuck? X squared minus 4. Can I do anything with that? What does that factor into? Can I factor that? X squared minus 4. What does that break into? Someone in the chat, someone chime in. Can I break apart x squared minus 4? Yeah, x plus 2x minus 2. Good, Bianca, exactly, right? This is a perfect square. Difference of squares. So I got x, x plus 2, x minus 2. So that's gonna be the top, x, and then x plus 2, and then x minus 2. Okay, so looking at this function now, we've broken it apart, we've done some factoring. What else do we notice? Hopefully we see, look at the bottom, look at the top, see if anything matches, and see if anything gives us a whole. And yeah, x minus 2 here is going to cancel. So there is going to be a hole at that location there. So I've simplified. I've got x, x plus 2 over x plus 10. And we know there's going to be a hole at x equals negative 2. Hole at x equals negative 2. What other type of discontinuity is there going to be? Look at the bottom here, right? This denominator, the fact that it's left alone, means we have a vertical asymptote at x equals negative 10. Those are the things we know about this function. We could learn a lot more. We could plug in the -2 and to find out where the hole is. We can plug in all kinds of other numbers to see where the graph is going. But we just, at its basic level, we need to know, where does the graph have a break? Where does the graph have a strange thing going on? And the strange things happen on denominators, right? When we divide by 0, those are where strange things happen. And the two kinds of strange things are a hole. If it cancels, we have a hole at that spot. And we have an asymptote, a vertical asymptote, or a discontinuity, an infinite discontinuity at these places where it doesn't cancel, at these denominators. So these two locations, at -2 and at -10, we know, because we have this understanding of continuity, we know that a hole is not a continuous spot, right? A hole means the graph doesn't exist there, right? The function does not exist. And we know vertical asymptote, it's a break as well, right? These are breaks in the graph. So when you are asked if a graph is continuous at these locations, you know that it is not continuous at these. Not continuous here. Because there's a hole is a discontinuity. It's a break. And a vertical asymptote is a discontinuity. It is a break in the graph. But we need to be able to explain it mathematically. Why is it not continuous? What definition, how do we justify, by using this mathematical definition, how do we justify our explanation? We cannot just say, oh, it's not continuous because there is a hole. Not good enough. We need to use this three-part definition to describe continuity. That's how we justify. We justify by saying one of these things is not going to be true. One of these things is not going to be true. So let's look at x equals 2. Is it continuous? Is this function continuous at x equals 2? Well, we know the answer is no, because there's a hole there. So we would say no. Because now we have to justify. Why is it not continuous? What piece of this definition is not correct? The piece that's not correct for us, well, we know that the limit from the left and the limit from the right, because it's a hole, we know the hole, excuse me, we know a hole reaches the same limit. So hole, we have the limit from the left equaling the limit from the right. So that's not the thing that breaks. The thing that breaks for us is if I try to plug in 2, right? If I try to plug a 2 into this equation, I'm going to get 0 divided by 0. And that means that the value f of 2 does not exist. So this is not continuous because f of 2 equals d and e. It is not continuous because the limit from the left and the limit from the right do not equal the value at that limit. Sure. So what we've done, we took our function, we broke it apart to kind of figure out what was happening with the function. Factored it out. We found some places where the graph doesn't exist. We found a hole when we canceled x minus 2. So we know there's a hole. Oopsies, what am I saying at minus 2? Sorry. That should be plus 2. We found a hole at x equals 2. A hole at x equals 2. Because it was minus 2, it was plus 2. Hole at x equals 2. Because we canceled, right? When we factored, we found one thing that canceled. That made a hole, that made a discontinuity at that function. Also, when we factored, we see that this x plus 10 on the bottom means we have a vertical asymptote, another discontinuity, at x equals -10. So we know our function, if we wanted to look at our function, we don't need a graph, but we can use one. If we wanted to look at our function, here's -10, and here's 2. I don't know what the function exactly looks like, but I know that at -10 there's going to be this vertical asymptote. And maybe my graph looks like this, and then like this. Come on now. And then at 2, when I reach 2, I know there's going to be a hole at that spot, and I keep going. So I know there is a break here and here. A break is a discontinuity. Discontinuity. A place where the graph doesn't exist, right? F of 2 does not exist. There's no value, right? It's a hole. There's no dot, right? If there was a dot filled in, then it'd have a value. But the function does not exist at that spot. It's blank. It's empty space. Same thing with -10. F of -10 also does not exist. Again, I don't know if exactly this is the graph, but this is the idea. So these two spots are places where the graph falls apart, where there's a hole or a break. So because it's a break, it's not continuous. But we need to use our definition. We need a mathematical explanation. Why is it a hole? Why is it a break? It's a break because our three-part definition falls apart. Not all three parts are equal. For 2, we know the limit from the left and the limit from the right are equal. Limit from the... Hold on, everyone. We know the limits are equal, but the value, the f of 2, is not the same as the limit. Those don't exist. The value doesn't exist. So the limits are not equal to the value. You have your bridge, your road in, your road out, your hole. The limits are not equal to the value. So you don't have continuity. You don't have a smooth curve. There's a break. So looking at now, let's try x equals 0. Is the graph continuous at x equals 0? Well, we know that there's only 2 spots where the graph is not continuous. Not continuous at 2, not continuous at -10. These 2 spots where it breaks. 0 is not a spot where it breaks. So we're pretty sure it's going to be continuous at 2. Pretty sure. But let's make absolutely sure. I need to test it. Test limit as x equals 0 from the left of f of x, and the limit as x equals 0 from the right of f of x, and the value of f of x. I need to know what all 3 of these are equal to. The limit from the left, limit from the right, and the value. So I test these limits. So how do I find a limit? Limit from the left, limit from the right. What are some strategies we had to find limits? Our very first strategy. How do we find limits? If it's a normal equation, if everything's okay, if it's like not weird, how do we find limits? Someone got to tell me. do we find limits? Yeah, Haley, plug in. Exactly. Yeah, you plug it in. If everything's okay, if the equation is normal, your first step is always to just plug it in. Plug in, test your limit, see if it works. So we got a 0. We're trying to get to 0. See where the function is at 0. Plug it in at 0. See what you get. So if I'm going to plug in 0, I'm going to get 0 cubed minus 4 times 0 over 0 squared plus 8 times 0 minus 20. So that's going to be 0 on the top, 0 times 0 plus 0, 0 minus 20 at the bottom, so that equals 0. The limit as x approaches 0 is 0. And I found that by plugging in. We did, look, we multiplied. What are you talking about, Angel? We multiplied 4 times 0. That's multiplying. 8 times 0. Easy peasy. Right? The math part's not hard. Again, the idea that's difficult is knowing what to do. Finding a limit, what do? Finding a limit, you plug it in. Plugged in my 0, got a 0. Well, that's the limit from the left. Limit from the right, that's going to be the same. Still approaching 0. Because I plug in the 0, right? Nothing weird is happening. I plug in 0, it's going to be 0 from both sides. So if my limits are equal to 0, I'm not finding f of x, I'm finding f of 0. I want to find out what is the location, what is the actual value of the graph at 0. If I try plugging in my 0, I'm also going to get a 0. Yes. For limit, well, they equal the same thing for this number. They equal the same thing for 0. They don't always equal the same thing, right? The point of so let me show you an example of that. This is a great question. Why would they be different, right? Let me go down here. So let's say you have a function like let's say f of x is equal to a system of equations. And you have x squared plus 2 when x is greater than or equal to, I don't know, 1. And you have x minus 5 when x is less than or equal to 1. Minus 5. Why is this thing not working? So for example here, right? If I asked what is the limit as x approaches 1 of f of x, well, you have two sides, right? You have one side that's this first equation as we're approaching from, like, this is all the x's less than, greater than 1. So this is from the right side, right? This is all the functions that are like, here's 1. That's all over here, right? All the stuff bigger than 1. And it's this function when x is less than 1. Over here, it's this other equation. So in this situation, you would have to plug in a different, right? You plug in a 1 to the top equation from the left. You'd plug in a 1 from the bottom equation on the right. And you'd see if they meet. So that's one example where you might do that. Another is our infinite situation. Our infinite situation where we have the break, right? If we approach the limit of negative 10, if we approach it from this side, from the left side, we're going towards positive infinity. Or if we're going from the right side, we're going to negative infinity. So it's only weird situations that require that, like, where the left and right will be different. Only weird situations, right? Maybe you have a graph that looks like this piecewise function. You have a graph that looks like this, that goes to here, and then jumps suddenly is over here, and then continues. Now your limit from the left and the right are different. But it's only because it's a piecewise function. Normal equations don't have this. But we have to sort of like, what we're doing, the reason we have this definition is so that we can mathematically define what it means to be continuous. You can just say, oh, well, it's continuous because it's like all connected. Because it's like all connected. What does that mean? Mathematically, how do we create a set of rules to describe connected or smooth? What does that mean? And the definition that we give it is, it's smooth when the left and the right and the value itself are all the same. That's continuous. Does that help explain some situations where we would have this, why this left and right is important? It's important in weird situations. It's important when we have something that's like off. Even this whole, it's important, right? That's why we have to have all three pieces come together, the value from the left and the value from the right, and the actual value itself, to show that these all these three things meet up together. That's how we say something is continuous. It's sort of, again, it's sort of obvious to think about. What does continuous mean? It means connected all together, smooth, no breaks. So if there's a break, you're not continuous. But we want to say it mathematically. We want to describe it mathematically, and this three-part definition describes it mathematically. We have a limit from the left, limit from the right, and the value itself. So again, last thing, okay, we're just about out of time, everyone. I know, we're getting there. Let me do this. Let me see if I can erase some of these things. All right. So again, for 0, we ask, is it continuous? Erase my graph. At x equals 0. And the answer is yes, because the limit as x approaches 0 from the left is equal to the limit as x approaches 0 from the right is equal to f of x. And this would be your answer. First one was no, because f of 2 does not exist. Anything that does not exist, you're not defined there. Same with -10. Just last one. Same with -10. Why is this not continuous? What rule can we say? Why is -10 not continuous? -10 did not cancel out. At x equals -10, we had what kind of discontinuity? What kind of discontinuity did we have? We have this vertical asymptote. And so because of vertical asymptote, we know that f of -10 does not exist. Just like the 2 didn't exist, because these are holes. These are places where it is discontinuous, places where the value does not exist. So when the value does not exist, we can't be continuous. And we just say that it doesn't exist. The value doesn't exist, and therefore because the value doesn't exist, we know it breaks one of the three pieces. All right, everybody. We're getting antsy. I see it. There's a lot to think about here. So here's my suggestion. Watch those videos. Check out the assignments. Think about it. what you need to worry about, like you can distill it to a couple really important things. One important thing is to find all the discontinuity pieces, right? We know how to do that. We factor it, we break it apart, we see the types of breaks, okay? Once you know where things are broken, it's very easy to tell if things are continuous or not. If one of the breaks, if you want to know if it's continuous in one of the breaks, you know it's not because it doesn't exist. That's it. That's all you have to say. If it is continuous, you test it. You test the limits. Limit from the left, limit from the right, and the value. And you'll kind of know, right? You'll already know if it's continuous or not, because if you have a function like this, you'll test from the left and the right, you'll plug it in. If you have a vertical asymptote, you'll know it doesn't exist. If you have a hole, you know it doesn't exist. If it does exist, you'll pretty much know. It's probably going to exist there. You find the limit from the left, from the right. If it's a regular equation, that just means plug in a 0. They're not going to be different. And the value, plug in the value, make sure it's all the same. And it's going to be, we're just showing a formal definition of the limit. Again, these situations you'll kind of know. Oh, we need this in all kinds of places. Remember, this is the foundation. We're building the foundation. We'll see where we go from here. All right, everybody. I'm going to call it for today. We'll go over this tomorrow. Continuity, again, this definition of continuity is extremely important. These three-part definitions, limit from the left, limit from the right, and the value itself. I will post this on Schoology. Yes, absolutely. For now, though, I'm going to call it. I'm going to stop recording.